Hi friends, here we are in chapter 4 and we're looking at section 4.7. We're going to talk about congruence transformations today. So we have a lot of vocabulary, but that's okay. It's not too bad. We're going to talk about we're going to talk about shapes and maintaining the shape but moving the shape around. That's really what it comes down to. And so we're calling them congruence transformations. Transformation is really just in mathematics when we talk about it, it's talking about the movement of a figure generally on the coordinate plane. So let's say I started off with this triangle ABC, and what I could do is take this triangle and I can literally bring it over here, right? A copy of it. And when I do that, I've created an image of that, and I'm going to call it A prime, B prime, C prime, okay? Same picture. Notice when I pulled it, it was like exactly the same picture, and I just slid it right over. And so that's a transformation. And so a transformation, we could have a transformation that is just a translation, and a translation is what I just demonstrated to you. Translation is just literally moving a picture from one place to another, literally moving it somewhere else, okay? So that's a translation. A rotation, I'm going to try to demonstrate that. Some of this I can't really demonstrate easily, so you guys will forgive me. But I'm doing this a little bit out of order. But a rotation would be for me to take that picture and literally rotate it, right? So I can rotate it just like that. It's still the same picture. It's still the same ABC, but now I've rotated it. So we've seen what a rotation looks like. All right. Let me put a check mark next to that. A reflection is a little bit harder for me to show you. So it would be like if I had this triangle ABC and then I wanted to reflect it over, let's say, the y-axis, then it would look like this. And you see my ability to be congruent is not happening here. But then I'd have this guy as a reflection. All right, makes sense? It's just like looking in the mirror. Isometry is really the same exact word as congruence transformation. So all of these are considered transformations, right? A way to move your graph or change your graphs. But these graphs are particularly special because they are congruent, right? They cannot change sizes. So the congruence transformation is also called isometry. And transformation is really just the idea of reflecting, translating, rotating. Sometimes in some textbooks, when we're not dealing with congruence transformation, we can also talk about dilation, right? And I'm just going to tell you about this now. I threw this same picture up here again. I'm going to take off some of the extras that I mistakenly copied when I was trying to copy it. And what you'll see is a dilation, which is not something we're studying, is when you can increase the size or decrease the size, but it's going to maintain the same shape. So that will be a dilation. A dilation can be kind of like a stretching or compressing. All right. Though that's not talked about here, I think it's something that you should know. Okie dokie. So let's see. So we got through these, and I use this language. The pre-image is the original guy, is the original picture, and the image is the changed picture. All right. So transformations are all of these guys down here. Pre-image, the original picture. Image is the thing that the changed picture. So this would be the image. And usually we use like primes to represent the image. Congruence transformation is just really what we're doing. We're making transformations by moving a congruent figure, whether it's flipping it, rotating it, or shifting it. Isometry is the same word. Reflections, like looking in the mirror, you flip it. Translation is just to slide from place to place, maintaining its same exact position. And rotation is what we did when we twirled it about. And if that didn't feel too well defined, this is in your text, and obviously here you can take a moment to read this, pause it, read it and see if it'll kind of solidify the concept for you. So now that we know the ins and outs of all congruence transformations, now we're going to be able to see if we can determine what kind of transformation we're looking at. And we have choices of reflection, translation, and rotation. So let's look at this guy. The pre-image is, let's just say this pre-image is the blue one, and the image is this green one. If we go from here to here, what would you say happened? It hasn't maintained its actual position, so it cannot be a mere translation. It is not flipped exactly over. It looks like it's twisted around, so this is going to be a rotation. Then we have this one. Let's say this is the pre-image and then we see it going over the y-axis and it totally looks like a flip. When we've got a flip, we know that's like the same thing when we look in the mirror. It is our reflection. And finally, part C, we see that we're maintaining the same shape. We start off at the blue, we maintain the same shape, we move this way, and we see that maintenance of shape is going to refer to a translation. Not too bad, right? All right, hopefully you guys did well with me. So in this real world example, what we're supposed to do is to refer to the information at the left, which you don't have, but I'll get it for you, and identify the type of congruence transformation shown in the diagram as a reflection, translation, or rotation. So I suppose this was helpful. Showing this image here shows us what the game is that they're playing. And the game is this very cool skipping game where you skip over the thing. And so what are we talking about if we think of the thing as the location of the ball as the original pre-image, then what's happening as it spins around a child's leg? It is a reflection, translation, rotation. Yeah, it's a rotation. All right. So here we are. We're going to verify the congruence of the congruence after a transformation. So triangle XZY has these following vertices and is a transformation of triangle ABC, which has these vertices. Graph the original figure and its image, and then identify the transformation and verify that is a congruence transformation. So I know you guys know how to graph, so I just pulled the graph out of the textbook. And then the verification of the congruence is basically figuring out the lengths of each side. Now, the triangles XZY and ABC are named in that way, so we should expect their congruence to follow the naming, meaning AB and XZ should be congruent, and XY and AC should be congruent, and BC and ZY should be congruent. How do we figure out congruence? Well, we figure out the lengths. And so this is going to be an opportunity for us to use the distance formula. Didn't think I was going to sing, did you? Yes, I did. So I think it's best if we just set up the situation as follows. Remember, the distance formula is equal to the square root of x sub 2 minus x sub 1, quantity squared plus y sub 2 minus y sub 1, quantity squared, all courtesy of the Pythagorean theorem. And so what we're going to have to do is find the lengths of A, B, and XZ, CA, and X and YX, BC, and ZY, and hope for the best. Hope that everything is good. So I've taken the opportunity to plug in some information, and look at here. I'm actually dealing with pretty much the same number. 6 minus 2, 6 minus 2, quantity squared, 7 minus 8, quantity squared is going to be the same as negative 7 plus 8 quantity squared, right? I'm going to get a same answers really. Same thing here, 4 minus 2, 4 minus 2, 8 minus 2, negative 2 plus 8, what? 6 minus 4, 6 minus 4, 7 minus 2, negative 7 plus 2. I'm done. We're not doing this. We're not going to figure out that the lengths are the same because we're using the same exact numbers ultimately, and therefore the lengths are the same. So we have verified it. So with our verification process complete, we are actually done with this section. So go ahead and try the problems. Let me know if you have any questions. Hopefully it won't be too bad. It'll make pretty much decent sense. And I look forward to seeing you and talking to you soon. Take care, guys. Bye.